I think isothermal I would have finished now, the calculation of delta S for that. That table is like just the all the formulas all together. Now let us start off with, kind of, I'll give you some question. I told you that I'm keeping some question pending there. So let us start off it, right? Okay, so I'm giving you a question, please do this. 5 moles of an ideal gas is expanded from 5 decimeter cube to 10 decimeter cube at 300 Kelvin. Find entropy change for the gas. Find it out, and you can keep your answer in terms of R, ln, whatever you are having. And here see, do not think that I have not mentioned reversible or irreversible, because you know that when I'm asking you the entropy change of the gas, that means I'm asking you to calculate deltas of the system. And we have seen that deltas of the system doesn't get affected whether you go for like reversible path or irreversible path. Calculate it and let me know. And you can also give me your answer in calorie also, calorie per mole Kelvin. Here, delta S system I have asked you. So the thing is, the formula will become NR ln V2 by V1. Number of moles I have given you 5, 5R ln, this is 10 upon 5. It will be 5R ln 2. Generally, examiner gives you in this format actually, right? But sometimes if they are asking you, kind of delta S to be expressed in calorie per mole per Kelvin or else joule per mole per Kelvin. So you should be able to do that also. So here I'll be writing this one as 5 into, this is 2 calorie per mole Kelvin. ln to log will be 2.303 into log 2. And basically I am taking this as approximately 2.3 and this is 0.3 only. So I'll be getting this one 0.69. So I'll be getting total answer as 6.9 calorie per mole Kelvin. So you should be like, comfortable solving in this way also. Normally I'm saying generally in this format it will be given, generally, but you never know the examiner. They can ask you for calorie per mole Kelvin or as joule per mole Kelvin. Now onwards, whatever question we are going to do, you can very well keep your answer in terms of R, ln itself. No need to worry about it. I have given you idea that okay, like this also you can do. Are you able to understand? Then I'll give you another question after this. Moving on to the next question now. 1 mole of an ideal gas is expanded from 10 atmosphere to 1 atmosphere at 300 Kelvin. Calculate delta S system, delta S surrounding and delta S universe under following condition. Under following condition. First one, if expansion carried out reversibly, if expansion carried out reversibly. Second one is if expansion is carried out irreversibly. And you can keep your answer in terms of R ln itself. Find it and let me know. Correct, Sham. So the first part here is for reversible. And this time I've given you pressure values. So delta S system, you know, it is going to be nR ln P1 by P2. And your P1 is 10 atmosphere. And P2 is 1 atmosphere. So you will be having your answer here as, and I've given you 1 mole. So R ln 10 will be your delta S system. And delta S surrounding is going to be minus of delta S system for reversible process. So in that case, it will become minus R ln 10. And delta S universe is just the summation of these two, which you are able to see it is going to be 0. So delta S system plus delta S surrounding, that will be 0 because it is R ln 10 minus R ln 10. It will be 0. Able to get this? Good. Then for irreversible, there will not be any change in delta S system value because it doesn't get affected whether it is. So I am writing here answer is R ln 10. Only thing is delta S surrounding is given by minus nR 1 minus P2 upon P1, and here it is 1 mole, P2 is 1, P1 is 10, so we'll be having minus 0.9 R. So ultimately delta S universe is going to be delta S system plus delta S surrounding, and I'll be having here R ln 10 minus 0.9 R. That's what is the expression which you are getting. Yes, good. Got this, everyone? Understood also? So very simple problems could be based on this. Now let us go for the next one. For isothermal we have seen, this time we are going for isobaric process. In case of isobaric process, we are having pressure constant. Now the thing is, if you are able to recall, I have given you delta S system, 2 formulas I have given you in the beginning for the calculation. That was NCV ln T2 by T1 plus NR ln V2 by V1. And the other formula was NCP ln T2 by T1 plus NR ln P1 by P2. Now the thing is, for isothermal process, we made use of both the formulas for deriving the formula finally for that particular process because temperature was appearing in both of them. Now for isobaric process, which formula I should be using out of those? Which formula I should use? Wherever pressure term is coming, I'll be using that formula here. So here I'll be writing, first of all, for reversible. So I'll be writing delta S system, that is equal to NCP ln T2 upon T1 plus NR ln P1 by P2. Since pressure is constant, this term will become 0 and I'll have delta S system, that is equal to NCP ln T2 upon T1. Now what will be your delta S surrounding? Minus of this delta S system. So I'll be writing delta S surrounding, that will be equal to minus of delta S system, and it will be written as delta S surrounding equal to minus NCP ln T2 upon T1. Write this out, everyone. Good. Write this out, and once you are done, let me know by writing done over there. See, previous and next slide I'm not going to do better. You know, things will be already shared with you. So you can check if at all you are left out somewhere. Second one, irreversible. When it comes to irreversible, delta S system is not going to get affected. So I'll be writing NCP ln T2 upon T1 only here. Then for delta S surrounding, all of you know that I'll be writing Q surrounding upon the temperature of the surrounding, and this time again system parameters, so minus Q system upon T. Now this is like we have used pressure here at constant pressure because we are dealing with isobaric process. Heat exchange at constant pressure is known as what? Delta H or delta U? Heat exchange at constant pressure. Is it delta H or delta U? Delta H. So I'll be writing in place of this minus delta H system upon T, and this is actually minus NCP delta T upon T, which can eventually be made as minus NCP T2 minus T1 upon T2. So this is the final formula which you have to remember, which I am writing here. Delta S surrounding, which is equal to minus NCP T2 minus T1 upon T2. Now, one thing to be understood here is T1 is the initial temperature of the system, right? T2 is the final temperature of the system, and T2 is actually the temperature of surrounding, right? Always remember, a system will finally acquire temperature according to its surrounding, according to what is the temperature of its surrounding. For example, when you keep, suppose you are at home, and if your mother brings a hot glass of milk, right? So when you keep it on table, so is the entire room becoming hot, or else that particular glass of milk cools down? Milk will be cooling down now according to whatever is the room temperature there. So room temperature, or else what I'm talking about is I'm talking about temperature of its surrounding. So eventually the system acquires whatever is the temperature of your surrounding. So final temperature of your system will always be according to the temperature of surrounding. Are you able to understand? So here simply I'll enlist the formula. Hopefully you people got it. So I'll write down here reversible, irreversible. We are making a small table. Delta system, delta surrounding. This is NCP ln T2 upon T1 minus NCP ln T2 upon T1. Here also NCP ln T2 upon T1, and here it will be minus NCP T2 minus T1 upon T2. Right? Please write this down, then we'll proceed further. Are we done writing? Done. Okay. Now let us move on for isochoric process. And in fact here, before even deriving for isochoric process, can you tell me on your own that what should be finally be seen in that formula? Cp should be replaced by what? Cp will be replaced by Cv. Correct. Absolutely correct. Okay. Somebody wanted me to scroll it down. I simply written this with irreversible. Delta S system is equal to NCP ln T2 by T1. Then let us go for the third process. So you are having here isochoric process. And for isochoric process, we know that volume is constant. Again here for reversible and irreversible, This time which formula I'll be using? This NCV ln T2 by T1 plus NR ln V2 by V1. Volume is constant, this goes away. So we'll be having delta S system that is equal to NCV ln T2 upon T1. Right? And delta S surrounding will be then minus of this delta S system. So I'll be writing delta S surrounding that is equal to minus of this delta system. It is only possible for a reversible process. So delta S surrounding will be minus NCV ln T2 upon T1. Finish writing this, then we'll proceed for the irreversible. Done? Okay. Now let us go for the irreversible here. For irreversible, I'll be saying, let us say delta S system doesn't change. So it will be NCV ln T2 upon T1. And delta S surrounding this time is going to be again Q surrounding upon temperature of the surrounding divided by minus Q system, but this time at constant volume, right? Hopefully you are able to follow why I'm writing minus Q system, because whatever surrounding might have gained, that system might have lost. And heat exchange at constant volume is known as what? Minus, this one will be delta U, right? So I'll be writing delta U for the system upon T, and I'll be writing minus NCV delta T upon T. It is exactly going on the same line what we have done for the constant pressure, except for the change there, that Cp has been changed by Cv. So our delta S surrounding formula has become minus NCV T2 minus T1 upon T2. So ultimately for reversible and for irreversible, delta S system, delta S surrounding here, so this is going to be NCV ln T2 upon T1 minus NCV ln T2 upon T1. This is again NCV ln T2 upon T1. And this one is minus NCV T2 minus T1 upon T2. So do remember, you are only having very simple formula here. So when you are revising, you refer to it, right? Write this down, then we'll proceed further. And once you are done, let me know. And after this, we'll see some question based on this. Finished? Good. Chalo, we'll proceed further then. I'm giving you a question. Give it a try. 2 moles of helium is heated from 300 Kelvin to 600 Kelvin at constant pressure. Find delta S for the gas. Identify, find the answer. Good. Sham, some answer is wrong, but 5R Ln2 is correct answer. This is monoatomic gas, right? And I've asked you at constant pressure. So actually delta S system you have to find out, which is NCP Ln T2 by T1, and Cp for a monoatomic gas is 5R by 2, right? So delta S system, what you are going to write down is 5R by 2, and in fact 2 moles I've given you, 2 into 5R by 2 ln of this is 600 upon 300. So we'll be getting actually 5R ln 2. Right, good. Many people have given correct answer. Likita, right? Okay. Next question I am giving you. 4 moles of an ideal gas, Cp value is 5R by 2, is heated from 400 Kelvin to 1200 Kelvin at constant volume. Find delta S for the system. Find out that. Variety of answer I am getting here, and not a single answer is correct. I have given you value of Cp, I didn't give you Cv. All those who have given me answer is wrong. Only Manas has given correct answer. Good. 6R ln 3 is the answer. Yes, Tejaswini also correct. Very good, Beta. So the thing is here, I have given you Cp value and I have asked you constant volume. So actually here what you have to get, delta S system is equal to NCV ln T2 by T1. First get the Cv value, Cp minus Cv equal to R. As such you directly also remember, no, that if at all Cp is 5R by 2, Cv will be 3R by 2. But if at all in case you are not able to remember, you can always remember this relation. Cv will be Cp minus R. 5R by 2 minus this R. You will be having basically 3R by 2. Now you place the values here. Do not do directly. Be careful what data is given to you. Delta system, I have given you 4 moles. Cv value ln of 1200 upon 400. So you're having here 6R ln of 3. That is your final answer. Able to get that? Good. Many of you have given correct answer. Wonderful, Anna. And those who have given wrong answer, identify where you went wrong. Okay? Only thing is here, Cp value only might have troubled you people. Okay? Shall we go for the next question now? I am giving you next question. 0.5 mole of an ideal gas is expanded from 1 liter to 10 liter adiabatically in vacuum. Find delta S for the gas. Find delta S for the gas. Amrut Anand, and moles taken wrong, beta. 4 moles I have given you directly. No, Rupa, you are a little bit hurry-burry. How many of you think that answer is 0 here? How many of you think that answer is 0? Yes. Sai has given correct answer. Wonderful, right? The thing is 0 is not the correct answer. You people are forgetting one thing, that I've also attached one more thing here, vacuum. So expansion in vacuum is nothing but adiabatic expansion in vacuum is actually isothermal process. So you have to use the formula of isothermal. Remember, I'm just writing that thing to recall, give it a recall for you people. From first law of thermodynamics, did we write down delta U is equal to Q plus W? This is adiabatic. For free expansion, this is 0. Delta U is 0, which implies NCV delta T is 0, which implies delta T is 0, and which makes temperature constant. This I've already taught you, I've given a note also. Right? So the thing is, now you will be calculating delta system is equal to NR ln V2 upon V1. So how many moles I have given you? 0.5 R ln 10. That should be your final answer. So only one person has given the correct answer, right? That means you people forget what has been taught earlier. Please be careful there. If at all I am not giving you vacuum, then 0 is correct answer. Not an issue. Likita, you also got the correct answer before me explaining this? Then it's good. Yes, are we done writing now? Okay, now let us move on towards physical significance of entropy. Physical significance of entropy. Because sometimes very simple questions could be asked from this particular section also. Now when it comes to entropy, you remember I have told you that it is a measure of randomness or disorderness which is present in any system, right? So basically sometimes the examiner may ask you by giving a situation or basically a reaction just to predict whether entropy is increasing or decreasing. Now there is one more way of kind of understanding entropy. We say that if the probability of finding something at a particular place reduces, we say entropy is increasing. I'll repeat it. If the probability of finding something reduces at a particular place, we say entropy is decreasing. For example, suppose the day when you clean your room, everything is neat and tidy and everything is present its own place, right? You're easily able to identify, okay, here where I have kept my pencil box, this chemistry book is there, physics book is there, right? You know that. After 3 or 4 days, the room starts to become messy again. So the probability of finding that chemistry book or else that geometry box, that reduces there, right? So your entropy, why? Because the entropy of the room has increased. Are you able to understand, right? So let us write down a certain thing here. So entropy is the measure of randomness present in the system. Randomness present in the system. And I'm going to tell you a few points here which will definitely help you out in predicting the entropy, whether it is going to increase or decrease in the given scenario. First point is, suppose if you consider a room where you have enclosed a gas. Now you start heating the gas. So what you are doing, are you increasing the temperature there? If the temperature increases, more random motion will start to happen inside the container, right? More thermal motions will be there, and because of that, what will happen to the randomness? It will increase, and I'll say entropy is going to increase. So I'll write down here, increase in temperature increases randomness, and that actually increases entropy. Able to get this, everyone? Second one I'm writing, increase in volume at constant temperature. This will also increase randomness, and that is also going to increase your entropy. For example, when you enclose a gas in a smaller volume, in a smaller container, there also randomness is there, right? But the thing is, if you make this gas occupy a bigger volume, so more random motion starts here, more randomness kind of gets created there, and because of that we say entropy increases. Why to go up to the gas also? You consider your example only. Suppose you are provided with a small room, one almirah, one cot, right? Suppose you are staying in hostel, right? So in that case, or else in your own home, suppose you got the smallest room. So in that case, what will happen? You will feel like to, kind of, since there is no space, so you will feel like to keep everything inside the bag or somewhere, so your things will not be cluttered. But suppose you got double than what is the present room, and there are so many shelves, so many almirah. So even the cap of the pen also will be here and there in one of the almirahs, right? So you will be making that more cluttered, more randomness there if more volume is provided, right? So here next one is increase in pressure at constant temperature. So if I increase pressure, volume decreases. Decrease in volume is associated with decrease in entropy, right? No, Jonathan, how it will liquefy, beta, unless or until you are not applying the pressure. How is it? Small container means it will liquefy on its own, huh? From when? Which principle of science, beta? We are just keeping it there. Then, when a molecule dissociates into its atoms, then also entropy increases. For example, if at all you are having H2, it is becoming 2H. I say that entropy is increasing in this process because earlier I am having basically one particle with me, which is one H2 molecule. Now I have broken them, I have got two particles, and because of that randomness is going to increase. No, Jonathan, that is a wrong concept. Next I am writing here, for phase change. We know that all the substances can exist in solid, liquid, gas depending upon what is the temperature and pressure. So out of a particular state of like different phases which are there, like solid, liquid and gas, so which one is most ordered form or most ordered phase for a substance? Most ordered phase for a substance. Most ordered I am saying, not most disordered, solid. So, and which is least ordered? Least ordered will be gas, right? So the one which is least ordered, that is going to be having associated with maximum entropy. So I'll write down here, entropy of the gas is much more as compared to entropy of the liquid, and that is also entropy of solid. Now next, sixth and seventh point, please take that as a conclusion, because those sixth and seventh point cannot be kind of digested very well in terms of randomness, because as such we define at your level that okay, entropy is the measure of randomness, disorderness. That's absolutely fine, but entropy carries with itself a much more deeper meaning, right? That means how energy and matter can be dispersed among the molecules in whatever possible ways. What is the probability of energy dispersal or matter dispersal? So that becomes difficult to understand at your level, right? So that is the reason you please take it as a conclusion which I am writing here. Okay. So the first one is, if atomicity of molecule increases, then entropy increases. Because if the complexity in the molecule increases, then you know that basically there could be different types of motion which you can attach with that, or else different degrees of freedom will be there, a translational motion, vibrational motion, rotational motion. So there will be like more number of ways by which a molecule can have its energy distributed. So for that reason, directly you remember the conclusion that if atomicity of the molecule increases, entropy is going to increase. So if I give you NO2 and NO, entropy of NO2 is going to be greater. For PCl5 and PCl3, for PCl5 it is going to be greater. Able to get it? Now similarly, if atomicity of the molecule is same, then higher molecular mass molecule has high entropy. So for example, if at all I say O2 and N2, OF2 and OH2, atomicity is same. O2 molecular mass is more, right? So just remember them as a conclusion. Acha, NO2 I have written, sorry, by mistake, beta. Yes, Tejaswini, thank you, beta. I have written by mistake here NO2 both. One is NO, another one is NO2. Harshvardhan also, thank you. Yes. Sai also, fine. So good that people are attentive, na? So atomicity, this is fine now. Printing mistake there, please consider that. Finished writing? Now I'll write down the next one here. For chemical reaction, first one involving only solid or liquid. That means there is no gaseous component involved here. So I'm writing here small change in entropy. Reason being, if at all gases are not there. Now the thing is, gases are not there. You are having only solid and liquid, right? So in that case, basically what is going to happen? Entropy is definitely going to change. But the thing is, entropy change will be less because the entropy of solid and liquid is much more lesser in comparison to gas. Okay. Now, next I am writing, suppose, for example, if I ask you entropy of carbon in the diamond form and entropy of carbon in the graphite form, out of diamond and graphite, which is much more ordered form of carbon? Let me know. Which is much more ordered form, diamond or graphite? You can write down D for diamond, G for graphite. Right, diamond is a much more ordered form. If it is much more ordered form, so its entropy will be less. Harita, how come much more ordered form, beta? Three-dimensional network is present in diamond, right? So the thing is here much more ordered form. So somebody, if at all, suppose I am giving you that carbon in the diamond form is getting converted into carbon in the graphite form. So in this reaction, is the entropy going to change? Increase or decrease? Entropy is going to increase or decrease here? Increase, correct. So entropy is going to increase. Good. Second one I am writing involving gases. Now when I write down involving gases means what? I have not written involving only gases. Right? In the above one, I have written involving only solid and liquid. There was no gas. Second one is involving gases means there is scope, there is chance that solid and liquid can also be present here. Now when it involves gases, it becomes easier that if gaseous moles increase, then delta S increases. That implies entropy is increasing. If gaseous moles decreases, this implies delta S lesser, and you will be having entropy decreasing. If delta Ng is 0, then what will happen to delta S? Delta Ng is 0, then what will happen to delta S? Delta S, do not think it will become 0. It is non-zero. For example, I am giving you one example. Let us take combustion of glucose, C6H12O6 solid, plus 6 O2 gas, giving you 6 CO2 gas, plus 6 H2O liquid. Here if you see delta Ng is 0, but still I say entropy increases. Here also I'll say that entropy increases. Reason being, you forget about the common factor. What is the common factor here? 6 moles of the gaseous reactant and 6 moles of the gaseous product. Okay. Then for understanding I am telling you, okay. Then what is left? Are you having 1 mole of the solid and are you having there 6 moles of the liquid which is getting formed? And out of liquid and solid, whose entropy is more? Of a liquid or of a solid? Of a liquid or of a solid? Definitely of a liquid. So can I think that basically entropy is going to increase? So actual reason is the overall total entropy of this 1 mole of solid plus 6 moles of gas is actually lesser in comparison to 6 moles of this gaseous product plus 6 moles of this gaseous product here. Are you able to understand? That's the reason we have written entropy is increasing. As such, as far as your level is concerned, they'll be just kind of restricting themselves to the reaction where delta Ng is lesser than 0 or greater than 0. This is just to kind of avoid any kind of misconception in your mind that delta Ng 0 doesn't imply that delta S will be 0. Are you clear about it? Having learnt all this, then we are going for, I'll give you some question. Are you done writing it? Tell me. Done? Okay. Now, predict whether entropy increases or decreases in the following. Sometimes they can give you like this also. Delta S is like positive or else delta S is negative or greater than 0, less than 0. Like that they can ask you. Okay. Now, first one I am writing C2H6 gas plus 7/2 O2 gas. As such, I am giving you a balanced equation. Make sure every time you are balancing an equation or else checking whether the equation is balanced or not. 3H2OL. Second one, 3C2H2. Third one, twice of NaHCO3 solid, giving you Na2CO3 solid plus CO2 gas plus H2O gas. Then X2 gas, it was present at 2 atmosphere. Now I am making it as at 10 atmosphere. Then I am writing a phenomena, mixing of gases. Then suppose I am writing here Hg solid, Hg liquid, Hg gas, CH4, C2H6, C3H8. Heating of this much you do, that is sufficient. All these examples you do, I am kind of bringing them all on the same page. And once you are done, let me know whether you have finished, then I'll discuss it. Done. Okay, fine. Let us see. Fine. We'll discuss it out. Need not worry. Now here for the first case, delta Ng, are you able to see it is decreasing? Because delta Ng is 2 minus, you're having 4.5, it is becoming minus 2.5. Right? So delta Ng is lesser than 0. That means delta S is lesser than 0 and entropy is decreasing. Here also delta Ng is negative. So delta Ng is less than 0. That means entropy is decreasing. Here gaseous moles are increasing. So delta Ng is 2 minus 0, which is 2. So delta Ng is greater than 0. That means entropy is increasing. In this case, I have increased the pressure. Pressure increase means what? Entropy is going to decrease. Mixing of gases, entropy is going to increase. Mixing of gases, entropy is always going to increase. Do remember, imagine like suppose in a room you had two partitions. Suppose there is gas A here, gas B here, right? And suppose if I ask you to kind of open this container and imagine those gas molecules to be like balls for the time being. So if I ask you from this container you kind of get a molecule, so definitely you'll be sure that it is gas B molecule only, right? And from this compartment you will be always getting gas A molecule only. But the moment I remove partition, both A, B, it will be like spread out, right? Mixed together. So if this time if I ask you, kind of get a molecule of A or get a molecule of B, you cannot. Because the probability of finding a particular molecule in that space has been reduced. So that's why we say that entropy has increased. Hopefully it is understood to everyone. Now, for this one, order will be gas, liquid, more complexity, more entropy in general. Fine, Ganeshwar, if at all you have kind of, thought like that also, then also it is good. Similarly, if at all, kind of you are making a solution, then also entropy increases, okay? Now let us move on to the next small topic here, which is delta S for reversible phase change. Now in this case basically, Muki, what is there in the first one beta? First one to only delta Ng na? Find out delta Ng. Here liquid is there, 2 minus, this is 3.5 plus 1, 4.5. So product minus reactant you'll be getting there. Delta Ng decreases, so delta S is decreasing, S decreasing. Now whenever there is a phase change, that means solid to liquid or liquid to gas, or else solid to gas. So basically that is what I'm talking about is a phase change. And always phase change will be happening at a particular temperature and pressure, right? And whenever we are talking about, suppose ice melting into, kind of water, or else water getting into that. So at 0 degrees Celsius, there will always be an equilibrium with each other. Little bit here and there, some pressure condition, it will melt. And here also it will freeze out. So they are going to be in equilibrium with each other. So that's why reversible. Now, let us talk about delta S system here. Can I write down this as Q system upon T? And since at a particular pressure and temperature it is happening, I can write down Q system at P, constant pressure. Now, heat exchange at constant pressure is known as what? Delta H. Now, depending upon what process I am talking about, that means if at all I am talking about fusion, I will be saying delta S fusion equal to delta H fusion upon melting point temperature, because fusion happens at that temperature. If at all I am talking about vaporization, that means liquid to vapor. So I'll be writing delta S of the vaporization, that is equal to delta H of the vaporization upon boiling point temperature. Suppose I am talking about sublimation, that means solid to gas. So I'll be writing delta S sublimation, that will be equal to delta H sublimation upon temperature at which sublimation is happening. Similarly, if at all I want to talk about basically this one, solid to solid transformation, which is basically allotropic transition. So I'll be saying basically carbon, suppose that transition will be happening at a particular temperature. So delta S for that transition is equal to delta H for the transition divided by temperature at which that transition is happening. So I'm going to write down the formulas here. You also can write down along with me. First one is fusion. So in fusion, basically, or else let me write down like this: solid to liquid, it is fusion, and I'll be writing delta S fusion, that is equal to delta H fusion upon the melting point temperature here, or else melting point. So this is melting point, and here it is molar enthalpy. Right? Always whatever delta H we are going to write down, they will be defined per mole here. Okay. Second one, liquid to gas. Basically, we are talking about vaporization phenomena. And here it will be delta S vaporization equal to delta H vaporization upon TB, which is boiling point here. Similarly, solid to gas, which is known as sublimation. So I'll be writing delta H sublimation, that is equal to delta S sublimation, that is equal to delta H sublimation upon the temperature at which sublimation is happening. All these enthalpy are molar enthalpy defined per mole. There should not be any doubt here. So temperature at which sublimation takes place. And the last one here, solid to solid, which I am talking about, is allotropic transition. So here we'll be writing delta S for that transition, that is equal to delta H for the transition upon the temperature at which this transition is happening. Like for diamond to graphite, that will be happening at a particular temperature, and there will be some enthalpy change associated for that transition. So we are going to write that. First finish writing this, then we'll see one or two questions based on this. QR I won't be having, beta. Sirisha, for one particular class it will be shared. If you are in the group, you can check there. Are you added in the group? Okay, let us try out some question here. Calculate entropy change for the process taking place for the following process. That process I'll be giving you. For the following process taking place at 300 Kelvin, X liquid to X gas, and delta H vaporization. Given delta H vaporization is 30 kilojoule per mole. And always remember, be careful that normally delta S will be given in terms of joule per mole Kelvin generally, right? You never know, examiner may kind of test by giving you in kilojoule also, but generally it will be in joule, so be careful with the unit. Please calculate it and let me know. What is the answer? We'll be writing delta as vaporization, because I have given you vaporization phenomena only, and I've also given you the temperature. So this is 30 kilojoule divided by 300. So when you get that, you'll be getting 100 joule per mole Kelvin. And people are getting 0.110 also. Arey nahi bhai. You have to get it in joule beta. That's what I said. Okay, good. Next question I am writing here. Find melting point of benzene. Tm is melting point, okay? Given delta H fusion is 10 kilojoule per mole and delta S fusion is 40 joule per mole Kelvin. Find it out. Correct. 250 Kelvin. Very good. Simply what you have to do, delta S fusion, that is equal to delta H fusion upon Tm, that is melting point. So we'll be writing this as delta H upon delta S for this fusion. And I have given you 10 kilojoule. Only thing is be consistent, or else be careful with the unit. You'll be getting this as 250 Kelvin. And sometimes you are calculating in Kelvin, examiner may express it in degrees Celsius, but it will be mentioned there. So be careful with that also. Okay. Let me give you one last question here. Calculate entropy change for melting of 10 gram of ice at 0 degrees Celsius given heat of fusion of ice is 80 calorie per gram. Find it out. If you wish to give your answer in fraction, then also fine. If you want to divide it, you can divide it and give me up to at least 1 decimal. Hmm. 800 upon 273 is fine. So delta S fusion has been asked. That is actually delta H fusion upon the temperature, melting point temperature. This is given for 1 gram and I have asked you for 10 gram. So basically for 1 gram 80. So for 10 gram it will be 80 into 10 divided by 0 degrees Celsius means it has to be 273. So 800 upon 273 calorie per gram Kelvin. Are you able to understand? Getting it, everyone? Now here I have asked you melting. Sometimes they may give you 10 gram of water and they can ask you entropy change for freezing. And they will give you date of heat of fusion of that particular kind of ice. So the thing is, you should understand delta H fusion should be replaced by minus of delta H freezing, because those two are just reverse. Are you able to understand? So you'll be getting your answer in minus. Understood, everyone? So in your test, start preparing from enthalpy of neutralization up to whatever has been taught so far. Okay. And I think lattice enthalpy and all those things have been asked earlier, and whatever is the order, it is according to NCERT. Need not worry about it. And spontaneity, I'll teach you along with delta G concept. So there should not be any trouble in what is the syllabus. I hope it is clear to all of you, right? So please write properly, write your examination. Wish you all the best. Study nicely. Thank you and have a nice day. I'll share the QR code. Our QR code is coming, do not worry. Sai, it's coming with on the way. Spontaneity is not there. Just now I said, no, beta. Spontaneity, would always have to say one statement, it will be done. What you didn't understand, Sai? What is the trouble there? Why I have multiplied by 10 kya? I have given you fusion. For 1 gram it is 80 calorie. How much you have to find out? For how many? For how much? You have to find out for 10 gram. So that's the reason. Total enthalpy there, na? So 10 into 80 you will do. Divided by what is the temperature there? Temperature is 0 degrees Celsius. You never take in 0 degrees Celsius. You convert it into Kelvin. Right? Fine. Hopefully everybody has done this. Rajani, some other data will also be given, beta. You don't have to do experiment there.